For this first problem here related to Ohm's law and circuits, I'm going to start with Ohm's law. We know the voltage of a battery is V. We know the resistance is R. So I can say V equals IR. And we're ultimately looking for the total charge that flows through it. But the first thing I can find is the current. And so the current is going to be equal to V divided by R. So that's the value for my current. I then know that current is equal to the amount of charge that flows through in a given time. So I can sub in for that current V over R is equal to the amount of charge over T, and I can ultimately solve for the amount of charge, and I get that that amount of charge, delta Q, is going to be VT divided by R. For question B, I'm looking for the total energy. What I'm going to find first is the power. Power is just voltage times current when we have a circuit. So the power, based off of V and R, is going to be the voltage times the current, which is V over R, or V squared divided by R. Now that I have that, I know that power is work, or the change in energy over time. So I can say that power is the amount of energy consumed over the time. Okay, again, that's just the same as the work done. And so I can say V squared divided by R equals the amount of energy used up over the time. And that means the energy that I use up in this circuit is going to be V squared times T over R. For this problem, I want to know what has more resistance, a 100-watt light bulb or 25-watt light bulb. In both cases, we're talking about power there. Okay, that's the power of the light bulb, which is the voltage times the current. So we're going to think about that, even though we're doing a conceptual explanation. That does help us with knowing the relationship between power, voltage, and current. The answer here is going to be the 25-watt light bulb. In order to figure that out, I'm going to think about this relationship between power, voltage, and current. In both cases, the light bulbs are connected to the same outlet, which means they draw the same amount of voltage. So the only thing that changes is the current. Okay, and so power is directly proportional to the current. So the 25-watt light bulb draws less current than the 100-watt light bulb. If we then think back to Ohm's law, V equals IR, all right, if they're both connected to the same voltage source, once again, that V is the same, the one with the smaller current is going to have the bigger resistance because current and resistance are inversely proportional. So therefore, the 25-watt light bulb, which draws less current, actually has more resistance than the 100-watt light bulb. For this next one, we have two of those circuits with missing information. In this case, we're trying to fill in the missing currents. So we're thinking about our junction rule. Whatever current flows into a junction must leave the junction. So I'm going to start right here, thinking about this part. We have 1.5 amps flowing through that resistor. That means 1.5 flows up to this junction. 0.7 goes that way. The remainder goes through resistor C, so that must be 0.8 amps to add up to that 1.5. Those two then come back together here in this junction, and we have 1.5 amps flowing through this branch. I'm going to think then about another junction here, and that's this one right here. We have the 1.3 amps coming down from that resistor, combining with this 1.5. And those two are coming together right at this junction to form a total current here through resistor B of 2.8 amps because they're going to combine. That 2.8 is going to kind of flow around here through the battery into resistor A. We can say that B and A are in a series. Okay, whatever current goes through B must continue through A, and so that means that A also gets 2.8 amps. Moving on to my second circuit here, here's my battery, some current leaves from it, we see 4.3 amps, comes up to this junction here, okay, so I'm going to first think about this junction, so we have 4.3 amps going this way, some goes down and goes through resistor D, the remainder goes straight through that 2.1 amp resistor, and so that means that we must have had 2.2 amps here go through resistor D. 4.3 went into this junction, 2.2 goes that way, 2.1 goes straight. That 2.2 or that 2.1 that went straight is going to continue on here through resistor F, so that means resistor F must also be 2.1 amps because there's no junctions here flowing through this part of the circuit. All right. The last junction I'm going to look at is this junction right here. We know that we had 2.2 amps flowing down through D. That's going to split here, so I'm just going to go that way through resistor E. The rest is going to go through this other resistor. So if 0.9 amps goes through the other resistor, that means the remainder, 1.3 amps, must go through resistor E. For this one, we're thinking about the voltages across each resistor, and for that, we're really thinking about loops and how every loop must add up to the voltage of the battery. So I'm going to start here with this inner loop here going from the battery around the circuit, just that basic inner square there. And what I see is we have an 11 volts across that one, 6 volts across that one, and so the remainder must add up to 25, which means that A must have a voltage of 8 volts to add up to 25 here. I'm going to take another loop then, so I'm going to take this middle loop here and go through B, through that 5 volt one, and through the 6 volt one. And so once again, we have 8 volts, we have 5 volts, that's 13, and 6 is 19, which means B here must have been 6 volts. And then we'll take that final loop there, going from the battery, through resistor B and all the way to the outside through C. Okay, and for that one, we have a voltage here of 8, we have 6, we have 6, so that adds up to 20, which means that one must be 5 volts. We also can see that these two that are in parallel have the same voltage, so that's another way that you could have figured that out. Moving on to our next one, we're once again going to look at some loops. So I'm going to start with this loop here, just that most inner loop going through resistor D. And so I have a 10 and a 12. I need to add up to 40 total here, so this one must be 18 volts, that resistor D there. I also know then resistor E needs to be 18 volts because these two are in parallel. And I could trace this loop here, and I would find the same thing. We have a 10 and a 12, that's 22, so we need another 18 to get up to 40. I'm now going to take the most outer loop here, going from the battery around to this 22 to resistor F, and then back. And so for that one, we're going to have 10 and 22, that's 32, which means resistor F here is going to have to just be 8 volts. For this problem here, I have two circuits. One is wired in series, circuit 1, the other is wired in parallel, which is circuit 2. And for each one, we want to find the total resistance, the voltage across each resistor, and the current through each resistor in our circuit. So I'm going to start with finding the total resistance here. So for the series one, that's not hard. We're just adding up the two resistors, R plus 3R, and we get a total resistance here of 4R. The next thing we want to find is the voltage across each resistor. But what I'm actually going to do first is find the total voltage of our, or total current of our circuit. I know it's connected to a voltage of V, and so I'm going to use Ohm's law. Using my total resistance, I'm going to be able to find my total current. And so I find that the total current, which is the current that leaves the battery, is just V over 4R. Okay? So I know that that's the current that leaves my battery here, and that's going to ultimately flow through both resistors. So that actually helps me answer question C. Okay? What is the current through each resistor? I know that the current through both of those resistors is going to just be V over 4R. Because in a series, both get that full current, the current that leaves the battery. In order to get the voltages, I'm then going to use Ohm's law. So for the resistor R, I'm going to say V equals IR. The voltage across resistor R, we'll call it VR, is going to be equal to the current, V over 4R, times that resistance, which is just R. So that means the voltage across resistor R is just V over 4. Alright. For the 3R resistor, I'm going to do the exact same thing, using Ohm's law once again. So the voltage across the 3R resistor is going to be V over 4R times the resistance of it, which is 3R. And so I end up getting that the voltage across the 3R resistor is 3/4 V. Okay, and that makes sense because these two add up to the total voltage of the battery, which they should because they're just a basic loop. Moving on to circuit 2 here, I'm going to find the total resistance. Here I'm going to use the 1 over RT equals 1 over R1, so 1 over R plus 1 over 3r. In order to solve for this one, I need to find a least common denominator. So I'm going to multiply top and bottom here by r, or by 3 for that first one. And so it's going to be 1 over rt equals 3 over 3r plus 1 over 3r, which ends up being 4 over 3r. And so when I solve for rt, I'm just basically going to flip both of them. I get that RT is going to be equal to 3R over 4. So that's my total resistance for circuit 2. The voltage for circuit 2 is going to be very easy. I see that each one of these resistors is in its own loop. So that means the voltage across it must be equal to V. Okay, both of them are going to have a voltage across them of V because they're in parallel. The current then, I'm going to use Ohm's law. So for resistor R, I'll say V equals IR. That's going to allow me to get the current across resistor R. In this case, the voltage is just V. The current, or the resistance, is just R. So V over R is equal to the resistance, or the current through resistor R. For the 3R resistor, same thing. I'll use Ohm's law once again. The voltage across it is V. I'm solving for that current through the 3R resistor, and its resistance is 3R. So when I solve for that, I get V over 3R is equal to the current through that 3R resistor. For this problem here, we have 3 different circuits, and for each one we want to rank the voltage across each resistor from least to greatest. So we'll take these circuits one at a time here. So for this first circuit here, what I see right off the bat is I see that B and C are in parallel with each other. And so I know that that means that the voltage across B and the voltage across C must be equal to each other. So I'll start with that. I'm then going to actually think about my current. We've talked some about how sometimes the easiest way to determine voltage is to think about current. So whatever current leaves the battery here is going to flow through A. It's then going to get to this junction and split. Some will go through B. Some will go through C before it comes back together here at this junction, and all of it flows through D. Alright, so that means that both A and D get the full current of the battery, but that current is split amongst B and C. And I know that Ohm's law tells me that V equals IR, and since all the resistors are identical, whichever one gets more current gets more voltage. So that means that both B and C have less voltage across it than A and D, and those two are equal to each other. And so that's going to be my ranking there. B equals C, which is less than A, which is equal to D. Moving on to circuit 2 here, what I see right across the bat is right here I have a short. Okay, the current comes up here from the battery, and it either can go through circuit E or it can take this shortcut. So that means that we have shorted out resistor E, and there will actually be no current, no voltage across E. So E is going to be the least. What I'm really left with then is my circuit is basically these two, F and G, in parallel, right? If we just take out this part, these two are in parallel with each other. So that means they're going to have the same voltage across them. So my overall ranking is going to be E, which is less than F, which is equal to G, because those two are in parallel. Moving on to circuit 3 here, I'm going to start by looking at this part right here. That right there is a break right before resistor J, which means that we basically have taken resistor J out of the mix. So J must have the smallest amount of voltage because no current will flow through it. There will be 0 voltage across it. I'm going to once again think about my current briefly to help determine my voltage. I know that current leaves the battery, goes through resistor H, and then splits here. Some goes down through I. Some continues straight and goes through K and L together, and then it all comes back together to go back to the battery. So that means that H gets the full voltage of the battery, or the full current of the battery, so that's going to be the greatest amount of voltage. All right, so whatever the ranking is, H will be the biggest. So we just need to figure out between I, K, and L which one is the most. We know that that current splits. We don't necessarily know that it splits evenly. So let's go back to thinking about voltage for a second. These two branches, here and here, must have the same total voltage across them. Okay, whenever we have two branches in parallel, the voltage across them must be the same. Another way of thinking about it is if we think about this inner loop, the voltage across H plus I by itself must add up to the battery. If we think about the outer loop, H plus K plus L must add up to the battery. So that means that KL together must have the same voltage as I. All right? And so therefore K and L will be less than I, and since K and L are identical resistors, thinking about Ohm's law, V equals IR, if they have the same current, they'll have the same voltage. So K and L will be equal to each other, they'll be less than I, all right, which is ultimately less than H. Another way we can think about this is this branch with the single resistor has less resistance than these two. All right, and so that means that more current will flow through this resistor here because there's less resistance. All right, and less current will flow through K and L, and therefore they have less voltage.